So, in this section, as I said earlier, we are going to do a simple derivation with one dimensional system, and we have done similar thing before when we looked at the harmonic oscillator as a spring connected with a mass of m1, and we said how does the spring move around and how we can calculate that as a simple harmonic motion. So, for that, and then we are going to look at the kinetic energy and potential energy term for that simple harmonic oscillator, and then we will also see can we use that in a very crude model, in a way very simplistic model for understanding the kinetic energy of the temperature in a VMDL situation. And then we will see can we use that even going further for the vibrational modes, and how does that connect with a simple Schrodinger equation with a simple wave function for a one dimensional system. So, that we can see the modes that are allowed for the vibrational spectroscopy. And then we will see one of the case studies that I have done in the vibrational spectroscopy or calculation of generalized vibrational spectra for ice system, which is a water molecule and in the solid phase. So, let us set up the derivation part here. So, I will start the document camera here for you, and so there it is, and so you can see what I will be deriving. So, now we start with a simple idea that we have a simple harmonic motion, and then we are going to develop that whole theory behind it using some of the ideas that we have here on the second order differential equations, which is our simple model to deal with. And last time we derived equation for a spring dash part, so it is nothing new, but now we are going to take this idea and use a simple harmonic oscillator. So, we start with our simple equations. We look at a system here. Let us draw this system. It is a spring connected on one side and there is a mass, and we will start with this system, and then we will also go to a diatomic molecule which say H and H. So, hydrogen atom connected between them is a spring, and we will see if we can connect with the vibrational modes. So, we start with our familiar equation. Newton's law of motion in case of spring is equal to minus k x, and minus sign essentially represent that depending on the force direction that you are looking at here. So, if you look at x is the displacement. So, let us say if this spring moves a little bit here. So, this is delta x. So, if you look at that becomes minus k delta x displacement. So, now let us look at for x dx over dt, we are going to represent that by x dot, and then d square x over dt square we are going to represent by x double dot. So, now we know that if we create this equation, we have m x double dot second differential is equal to minus k x. We did that earlier. Now, m x double dot, if I bring it on the other side of the equality sign, k x is equal to 0. So, now we can put a generalized solution. Because it is simple harmonic motion, we call it simple harmonic motion SHM, and that would be x is equal to, let us say, a cos omega t. We are just looking at the oscillating angular motions here of the particles. So, we have a cos omega t plus b sin omega t. So, that is our page number 1. Now, let us go to the page number 2. So, now here if you look at the solution to this equation, if we do a cos omega t, which we did earlier, becomes omega is equal to under root of k by m, where k is the force constant or what we call spring constant, and m is the mass of the particle. So, now if you look at this oscillation angular angular looking at the frequency of oscillation, then we can say what is the frequency of oscillation V. Then we can connect that with the omega over 2 pi, because we are looking at 2 pi radians. So, in that case, now if we plug that in terms of the angular frequency, then we have 1 over 2 pi under root of k by m. So, this becomes our what we call is oscillation frequency. So, let us call it frequency of oscillation. The reason we are going with this is because we want to come up with the vibrational frequency, which is a frequency of oscillation. So, if you look at for the same equation now, mx double dot plus kx is equal to 0, that is our characteristic equation. Now, we are going to take this further with a simple solution, where we say we just take the cos a cos omega t. So, that looks like a function where we start cos 0, this is 0 is 1. So, this is 1, it comes down, fluctuates like that, and this we are looking at this lambda, which is the wavelength. So, wavelength. So, this is a solution of harmonic motion, which is going with a simple solution of a cos omega t. So, if we look at the amplitude of oscillation as a, then we can plug in x is equal to a cos omega t. So, if we plug that into our equation for the second order differential motion of what we call simple harmonic motion, SHM for spring, then it comes out to be kinetic energy part k is equal to m x dot square by 2, which is nothing but half m v square. And so, if we plug a cos omega t solution into the this particular equation here, where x is equal to a cos omega t, and then we do the first differential and square it, then it comes out to be a square m omega square by 2 sine square omega t. It is just squaring and differentiating one time this function a cos omega t from your simple trigonometry. So, that is the kinetic energy k, and in case of if you look at the potential energy V, you have to integrate from 0 to x, again minus sign, which is you have kx and dx. So, we are going to do that. So, it becomes positive kx square by 2, again simple integration. So, if you look at these two terms, now you have a full energy equation where it is a square m omega square by 2 sine square omega t plus kx square by 2. So, this is our energy total, kinetic part and the potential part. So, this is our 3. So, now with this understanding, now we are able to look at what will be the behavior of the two terms. So, we are looking at V, which is equal to kx square by 2, that becomes V is equal to a square k cos square omega t by 2, and kinetic energy was a square m, which is the mass, omega square by 2, this is a constant term, sine omega t, sine square omega t. So, now you can see the behavior. If this is 1 and this is 1, and we are looking at kinetic energy and potential energy, then we start cos, we are looking at the potential energy, which is starting at 1, and then we are looking at the other part of it. So, if we just generally derive it, so let us say we start with kinetic energy, which is sine square. So, sine 0 start like that, go like that. So, if you look at potential energy, then we will start opposite of that. So, if it goes, so this is going to be 0 and this is going to be behavior. So, if you look at the constant of that, this may be kinetic energy, this is potential energy. So, when what it says is that when V is V max is equal to 1, K max is K becomes 0. So, it's opposite, K is equal to 0. When K is maximum, V is equal to 0. So, these are essentially opposing factors with the kinetic and potential energy. So, now we go one step further and see what is going on in a quantum solution. So, in this case, we are going to do Schrodinger equation. So, let me just write this Schrodinger equation, h square over 2m. Let me write down O Dinger's equation. And this is the first time you are encountering in this course the quantum mechanical function. So, this is a wave function dx square plus E minus kx square by 2. This is the wave function is equal to 0. Using V from equation above that we derived and putting that into the equation and the boundary condition where sigma 0 is equal to 0 as x goes to plus or minus infinity, then we know that psi 0 wave function is equal to n e to the power minus alpha x square. We look at the exponential solution now, and where alpha is equal to under root k m divided by Planck's constant h Planck's. Now, in this case, if I look at then E0, then we can calculate using the Schrodinger equation the energy at 0 level will be Planck's constant by 2 under root of k by m. So, this is your first level of energy level. In as you know, in quantum mechanics, you have to have energy levels. So, now we are looking at this energy level. And then if you go further and solve for d square psi over dx square, then we get the solution which is n alpha square x square minus alpha square. We already defined alpha e to the power minus alpha x square by 2, which is the trial function we have used here. So, we are now able to expand it, and what we are coming back with here is a very nicely derived equation for one dimensional Schrodinger equation for a spring dashpot system, which is equal to n alpha square minus x square minus alpha square, and we multiply this alpha x square by 2, expanding that becomes n. Now, we are just multiplying different factors here, h square by 2m. Now, we take the first term minus x square. So, we are plugging that into our original equation. So, that is the first term, e to the power minus alpha x square by 2 plus the other energy term where n, we are looking at e minus k x square by 2 and multiply that by the same exponential function, which is alpha x square by 2. So, if you look at here, we are looking at n property is equal to alpha over pi to the power 1/4. So, if you look at that, and also if we think minus infinite to infinite, if we do e function of minus alpha x square, that gives us under root of pi by alpha. Then we have a very nice solution for vibrational energies now and their levels. So, if you look at here, now we get equation alpha square h square over 2m minus k by 2 plus, and this x square, this is x square plus e minus alpha h square by 2m is equal to 0. So, that gives us energy level any energy level n is equal to n plus or minus half h under root k by m. So, this is what we were looking for. This is a simple solution where n is equal to 0, 1, 2, 3. So, what does that really mean? So, in this case what we are looking at is, let us say if we draw the function phi at different n's. So, let me put that E0 E n is equal to h over 2 plus or minus under root, let me just do it right. So, let us take that out. I am going to put it right here. So, you look at E n is equal to n plus minus half. These are the energy states h under root k by m. So, now we can look at the levels. So, when n is equal to 0, n is equal to 1, n is equal to 2, what are the energy states and how they will look like as a Gaussian term. So, when n is equal to 0, you are looking at it becoming purely Gaussian term. So, that is where you will look at the peak, which is coming out like that is at n is equal to 0. For n is equal to 2, you will see 2 of them. So, you are going to start with this kind of distribution. For n is equal to 2, you will have starting from here going down, then coming up again and going down. And if you look at n is equal to 3, now you have another modes of vibration where you are looking these different vibrational modes. So, this is where we are looking at different energy levels. So, let us say if this was energy level, this is ground 0, this is n is equal to 1, n is equal to 2 and n is equal to 3. So, what does this all means here is that we are able to now understand different modes of vibrations, and these modes of vibrations are now connected to the quantum numbers of the state, which are allowed state for energy to jump from one place to another. So, I have given you a whole bunch of equation to think about. We started with the simple harmonic motion and then did the similar thing with Schrodinger equation with the simplest function, which is called wave function, and then we derived it and understood that the energy can exist in various levels. And so, if you go to level n is equal to 0, n is equal to 1, n is equal to 2, 3 and 4, you see different modes of vibration, and those are the allowed state in the spectroscopic model, and those are the states that you will observe when you do a molecular spectroscopy. And the molecular spectroscopy essentially, then you have to, let us say take two particles, then you can create a reduced mass, and then you can derive the same equation where you know what are the allowed states for vibration you expect, and then by a spectroscopy you can look at that. The beauty of this whole analysis here is that we can use molecular dynamics using velocity autocorrelation function to calculate the vibrational spectra, which I will cover in the next section. Thank you.